Then welcome everybody to this week's episode of SPCL Bcast, where I'm super happy to be able to present you Prasanna Balaprakash. He is a scholar at Argonne and a long-term collaborator and friend, of course. And so Marcin is going to introduce him more formally now that we can see what he has achieved.
Yeah, so Prasanna is a computer scientist with a joint appointment in the Mathematics and Computer Science Division and the Leadership Computing faculty at Argonne. He is a recipient of the US Department of Energy 2018 Early Career Award. And prior to Argonne, he worked as a Chief Technology Officer at Mentis SPRL, which was a machine learning startup in Brussels. And he was a recipient of the European Commission's Marie Curie and Belgian FNRS Aspirant Fellowship during his PhD. Thank you for being with us. It's a pleasure to have you here. We will start the talk first and then follow up with a Q&A session. Everyone is welcome to put their questions into the chat, and I'll then read them after the talk. So without further ado, I will hand it over to you.
Okay. You see my screen okay? Great. All right, good evening, everyone. People from Europe, and good morning, people from US if you're tuning in. It's a pleasure to give a talk at SPCL. You know, this is a lab that we look up to for all the great work that is coming out, and keep doing that work and keep inspiring us. So it's a great opportunity for me to give a talk in the lab today. And I'm going to talk about design and development, more in particular, how to automate the design and development of deep learning. So HPC, high performance computing, has been sort of revolutionizing deep learning training, reducing the time to solution, time to training, and inference, and so on and so forth. But I'm going to talk about how we can use HPC to automate the design and development of neural networks and deep learning methods. And more importantly, I'm going to focus on one of the key challenges that the machine learning community is facing, which is the uncertainty quantification in deep learning. And I'm going to tell you how to solve that important problem using HPC. So it's not just about making the training faster or inference faster, but HPC can provide solutions to address solutions to pressing problems in machine learning, more foundational problems in machine learning. Okay, let me go from there. To begin with, I come from a Department of Energy run lab called Argonne National Lab, and we have several complex systems. And these complex systems in the DOE, they accelerate scientific discovery from nanoscale to exascale. Examples include advanced photon sources. This is the sort of the ring facility that we have. So think of this as a sort of a smaller version of CERN, but here the purpose is different. We send X-rays around this ring to study the internals of the materials and material properties, characterization of materials, and so on and so forth. Similarly, we have another facility called ATLAS, which we use to understand nuclear physical phenomena. Okay, I'm trying to move this window. Okay. Yeah. And we consider big HPC platforms, such as the one that is going to come at Argonne Leadership Computing Facility, such as Aurora, the one that is already in Oak Ridge National Lab, the Frontier, the exascale machine, right? So these are all complex systems because they have multiple components, they are interconnected, and we have to analyze them, we have to study them, use them, control them to solve challenging science problems, and many other such type of complex systems. Artificial intelligence, in particular machine learning and deep learning, has found its way in many of these science domains. They are used for modeling, these complex systems. So modeling here means, again, going back to this example of HPC platforms, let's say, modeling the performance of an application running on HPC platform. That's the bread and butter of our research, right? So how to do this sort of modeling across systems, right? Analytical performance models have tasted a lot of success, but increasing complexity of these type of systems are forcing more and more towards machine learning and deep learning. Why we need to model them? Because once we model them, we can predict the performance. We can ask what if questions, changing the configurations to ask like, okay, what are the different types of performance that we can get with the different configurations? The same thing applies for fusion reactor sitting in D3D in a General Atomics, where we have to model this entire fusion reactor. And once we model them, then we can predict when the plasma within the fusion reactor can go unstable, or whether it is stable, and so on and so forth, right? So modeling plays a central role across many different types of complex systems. Models can also be used to optimize, right? So if we have a system, a surrogate models of a system, or a model of the system, then we can go and optimize that model and take the final configuration and use that configuration or optimized configuration within these complex systems. So a fine example is, let's say we have a performance model of an application on a platform, right? On a HPC platform. Then if we have a performance model, then we can use a performance model to optimize the parameters. And once we optimize that, then we use those parameters to run the application on the platform. And finally, we can use such model to control the complex system. Again, think of a surrogate model for the entire HPC system, right? And if we have such a surrogate model, then we can develop control strategies, proactive and reactive control strategies that look at the state of the system and make decisions and make, okay, these are the type of jobs that I'm seeing, how I can schedule next set of jobs. Or within a node, this is the type of computation that I'm seeing, the memory, the data movement I'm seeing. How can I use that information to prefetch the data at different stages of the memory, so that I can reduce the time to load the data, right? So there are many interesting things that we can do in terms of modeling, optimizing, and controlling complex systems. All right, so here is an example, or a set of examples of diverse applications at Argonne, just at Argonne. So it was pre-pandemic, we made a survey and see what are all the different types of applications that we have in the lab where we are using machine learning. And we came up with 100+ applications, that is 2-3 years back. And this is increasing at a rapid pace as we move forward. And here is a set of examples, starting from laser, climate modeling, parameter extraction, atom probe tomography. All these are sort of machine learning applications where you have to collect the data, build a surrogate model, and do something with that type of with that surrogate model, right? So this is in contrast to the commercial space where you have vision and language models, where you can build a large vision models or a large language models, and then use those models in the downstream task to sort of solve specific set of problems. Here we have to build surrogate models for each application, for each modality. Of course, there are possibilities to combine these models, but many of these are totally different. In this case, for example, the weather has nothing to do with atom probe tomography in the X-ray characterization at the APS, right? So this is one of the biggest challenges that we face, the diversity of the applications within the lab. Now think about across the lab, across other labs in the world, the application is mind-boggling, that we cannot just build one single monolithic model and solve all these problems. Okay, so if we think about neural networks as sort of a surrogate models, right? So I'm going to talk about neural networks in the rest of the talk, but this applies to many other machine learning models, right? If we have to design a neural network, so an example here is a graph neural network, which we designed for molecular property prediction, which takes the graph structure of the molecules, and then we have message passing layers within those neural networks, and then we have to predict the property. Okay, given this, we can take the training data, train the graph neural network, and then predict the property of the unseen molecules, right? For this simple graph neural network, the number of possible design choices is up to like 10 to the power of 10. So think of this as a number of Lego blocks, which we have to put together in such a way that it's not any sort of shape is fine, but a certain shape will work well, right? So that's the sort of problem that we are dealing with. So it's a searching for a needle in the haystack or few needles in the haystack, and given that we don't have a lot of data, right? So in many applications, we don't have a lot of data. Even if we have the data, we don't have the labeled data, right? So how can we develop neural networks in the face of such large design space? How it is currently done? Often it's trial and error. If you go and ask like how and why certain type of architectures were designed, it's always like, okay, I tried this, it works, so I'm going to stick with it, right? It's a trial and error, and trial and error means it's also time consuming. So think about each possible iterations one has to make in developing these type of models. So it's also called graduate student descent, as I know it's a sort of a joke to the stochastic gradient descent, right? So one way to think about automating the whole process is the process of designing neural networks is how, what are all the degrees of freedom in neural network design, right? And at a very high level, there are two classes. One is algorithm hyperparameters, and the other one is architecture hyperparameters. Algorithm hyperparameters means, okay, so you define the network and then you sort of identify what are all the right parameters that can allow you to reach good weights for the particular fixed neural network. In that case, the kind of hyperparameters that decide decide high performance model weights are stochastic gradient, the type of optimizers, like, goes from stochastic gradient descent, RMS prop, Adam, and so on and so forth, learning rate, mini batch size, and so on and so forth. So essentially, you fix the neural network architecture and you sort of say, okay, what are all the training parameters that I have to optimize to make this neural network topology better? Then you have the architecture hyperparameters, where the degrees of freedom are the hyperparameters decide how the network look like, right? So that is one level higher than just tuning the training hyperparameters. And this goes from number of layers, type of layer, and activation function, dropout, and more importantly, skip connections. As you have seen in many of the recent neural network architectures, residual connections or skip connections play a central role in achieving good performance. And coming up with the right skip connections, if you look at any type of neural network with skip connections, it's always regular. And have you ever wondered why it's always like symmetric or regular? That is because it's easy to design in that way. No one has tried to do it in an asymmetric way. And again, if you take an autoencoder, often the autoencoders are symmetric. Have you ever wondered why autoencoders cannot be symmetric, why autoencoders can be asymmetric, right? So the encoder part and decoder part, often the layers are sort of the same, the inversion of it, right? So there are many things that can be done, going from the regular type of neural network designed by hand. So one note about the skip connections, right? So why I emphasize skip connections is for this reason. So this is the loss surface without the skip connection on ResNet 56. So ResNet 56 loss surface, if you train it, if you configure the network without skip connection, your loss surface looks like this, right? So this loss surface is very, very hard to train because there are multiple local solutions and they are low performing local solutions, right? On the other hand, once you start adding skip connections, your loss surface will become a lot more smoother. And this is really nice because once we have such a kind of loss surface, then the training is really easy. You can get into a local solution. This is again a local solution, but a high-performing local solution really, really fast, right? Incidentally, this is not just for residual networks in images. This also happens in physics-informed neural networks when you start adding constraints to the loss function. Physics-informed neural networks are the neural networks that we use a lot in science applications because we know the underlying PDEs and we know the sort of the PDE constraints, and we include those PDEs into the loss function so that neural network not only predicts something, but it also satisfies the underlying physical laws. But we all know that any optimization problem, once you start adding constraints to the loss function, your loss surface will become bad. And one way to address such type of problem, in particular with physics-informed neural networks, is to add skip connections and make the loss surface much more smoother, right? Okay, so now we have covered like the degrees of freedom, right? So now if you define the degrees of freedom and then say this is one example where say, okay, if we define that search space of residual connections or skip connections, and then if we sample some neural networks from that space, this is a potential neural network that you can get. And I want to take a note. I want you to notice this aspect of residual connections, right? So there is no limit. You don't need to have a symmetric or a systematic skip connections or residual connections. It can go from any layer to any layer. Of course, what is the right skip connection? That's part of the search space, and we have to search through it. Of course, it's a difficult problem, but we parameterized it. And now, if you worked in TensorFlow or Keras, this is a visualization of a neural network. And from the same search space with the different possible skip connections, we can build a diverse set of architectures, right? So from the same search space, this is of 68K parameters, this is 344K parameters. But look at the type of skip connections that are possible, right? So this one can go from here, this one can go from here to here, and this layer can be connected to this layer, right? The flexibility in such type of residual connections is a real advantage when we talk about making the problem a lot more easier. Okay, great. So we have so far what we have defined is the kind of degrees of freedom, right? What are the potential things that we can parameterize and search over? And now we can then formulate this as an optimization problem, right? So then we can think about how to solve it. So mathematically, the hyperparameter tuning or the automated design problem can be formulated as a bi-level optimization problem. At a lower level, this is a problem that we all do every time, right? So take a network and train. So the lower level problem is performed on the training data, and it minimizes the training loss, right? For a given architecture and for a given hyperparameter. The upper level problem consists in changing the architecture hyperparameters and the algorithm hyperparameters, where capital HA and capital HM are the hyperparameter space, whereas HA and HM are a specific realization from this space. So essentially, you find a combination of architecture and algorithm hyperparameters, you fix the neural network, and train that neural network. So the training is a lower level problem. The upper level problem, so once you train it, you evaluate that neural network on the validation data, not the test data, note, underline that, on the validation data, and that validation metric, here the validation accuracy, is something that we have to maximize. So that's the upper level problem. Okay, so lower level problem, upper level problem. Okay, so there's a validation accuracy that we have to minimize. Okay, so to that end, okay, how to solve this problem? We have been developing algorithms and software, scalable software, to solve that bi-level optimization problem. And the software that we developed is called DeepHyper, and it consists of two major components. One is search component, which has algorithms for hyperparameter search, algorithms for neural architecture search, and algorithms that can do both joint neural and hyperparameter search. The key component here is a workflow system that is based on Ray for smaller scale and MPI for larger scale, where these backend essentially help us to evaluate multiple neural networks in parallel and help us to sort of search over different types of parameters. Okay, the algorithm that we developed and sort of focused within DeepHyper is a Bayesian optimization. a quick primer on Bayesian optimization. So this is based on this so-called probabilistic model. So you have an input and you have an output and you have some evaluation. So consider input as a input parameter configurations or hyperparameter configurations, and output as your validation accuracy. Okay, so you evaluate some parameters and then you evaluate the you sample some parameters, right? Hyperparameter values, and then you train those neural network. And now you have the validation accuracy. So once you have that validation accuracy, you can build that probabilistic model. And in Bayesian optimization, it's not one function that you fit through those evaluated points, but multiple functions. And consequently, what happens is wherever you evaluated those points, your uncertainty will be zero because the model is certain, because you have the ground truth there. Once you move away from the ground truth, different functions can have different values based on whatever they have as a prior, right? So essentially, the farther you move, your uncertainty will become larger and larger. And this property is leveraged within Bayesian optimization to search through different parameters. And that's something that we will see next. This is how it is done. So you start with some randomly sampled hyperparameter configurations. You train the model, you take those values, right? And then you fit that probabilistic model. And then using that probabilistic model and the uncertainty, you decide where to sample next. So once you decide where to sample next, for example, oh, here is a large uncertainty. So I'm going to sample here because by doing so, I will get the ground truth here, and that will improve my validation accuracy, right? Or here is a point that I found which has a maximum validation accuracy. So I'm going to sample more around this point, right? So that is called exploitation. And the one where you sample with high uncertainty is called exploration, because you explore the space to reduce the uncertainty so that your model becomes better. Once your model becomes better, then you can make much more informed decision. On the other hand, exploitation is something that you have evaluated certain points, and now you want to go and sample from regions where you have found high validation accuracy, right? Because that will increase the probability of improvement. And this is done in an iterative way, right? So if it is done in an iterative way, then what you can see is the uncertainty will go smaller and smaller. So essentially, you will start approximating the true relationship between the hyperparameters and their validation accuracy values, and use that to improve your sampling efficiency. So what is the problem? Many Bayesian optimization methods are sequential. They care a lot about sample efficiency in the sense that you don't have a lot of evaluations to make. So you are allowed to perform only fewer evaluations. So you do one evaluation at a time. And most of these Bayesian optimization methods are sequential. The problem in Bayesian optimization is that its scalability. It won't scale. In particular, if you have thousands of GPUs available for you to do this architecture search or hyperparameter search, how can you use 1,000 at the same time, right? Because if you are doing one at a time, you are wasting the resources. By using 1,000 GPUs, how can you reduce the time it takes to do hyperparameter tuning and then sort of improve the accuracy of the models that you find? So that's the area that we focus: how to scale Bayesian optimization and how to make it work on big machines like Aurora and Frontier, and use that to automate the design and development of neural networks. Okay, so the methodology that we took is called asynchronous multi-point evaluation. It's also called Kriging Believer and constant layer. I will tell you why it is called constant layer. But before going into that, the key here is, the key challenge with Bayesian optimization is the scalability. That is, you cannot just scale because the Gaussian process regression, which is often used within Bayesian optimization, doesn't scale well. It has a cubic complexity. So the more points, more data you have, it takes a lot more time to retrain that model and fit the model again and again. So the first thing that we did is to get away from Gaussian process regression within Bayesian optimization and use more faster methods such as regression trees. So regression trees are nice because it easily handles mixed integer space. With the Gaussian process, you have to do a lot of pre-processing to make it work for mixed integer space. Note that most of our parameters are integer, real. Most of our parameters are integer and categorical. Few are real. So there are a lot of discreteness in the search space. So the regression trees are really good at handling those type of parameter space because the methodology itself allows to do that. And the second thing is, if you have 100 regression trees, you can parallelize each tree within a core. So you can really get a good parallelization with regression trees as opposed to Gaussian process regression, which you have to do a matrix inversion, and we all know matrix inversion is a bottleneck, right? For very large matrices. And then it also requires minimal tuning. It often works out of the box, as we have seen in many of the Kaggle competitions. Regression trees are the state of the art. Because it's the data, right? So it's really good for smaller, medium range data, and that is perfectly fine for hyperparameter tuning, because here we are not dealing with millions and millions of neural networks. We are dealing with thousands of neural networks for which this method is perfectly fit. Of course, we have to do something to improve its uncertainty quantification, because Gaussian process has a very good uncertainty quantification capability, whereas regression trees does not. So we have to do some modifications to this method to improve its uncertainty quantification. Now, once we had this model, then we had to use this model to do multi-point asynchronous multi-point evaluation, which is nothing but, let's say you have 100 GPUs and you are evaluating 100 models. At any point of time, let's say 30 models finish their evaluation and come back. Now you have to go and fill those 30 GPUs immediately. Otherwise, those 30 GPUs will be idle and you are eventually losing out the resource utilization. So how to generate those 30 configurations in a minimal time is the key to scalable Bayesian optimization. So now here you have a model and an acquisition function. So the model is a regression tree, and acquisition function is the one that sort of trade-off between exploration and exploitation. So let's say if you have k configurations to generate, let's say again the 100 GPUs, 30 finishes at the same time, and now you have to generate 30 configuration. How to generate that? You select a point that maximizes this acquisition function, and then you predict the mean and the standard deviation of that model, because let's say once you select a hyperparameter configuration, you can use the model to predict the mean and standard deviation. That's what the probabilistic model is going to give. There you are going to take that mean and lie to the model that its prediction is right. Okay, that is the key. If you say that, then what happens, and retrain the model, what happens is that whatever the point that the model selected, its uncertainty will become 0. So it will go and look at another region where it has higher uncertainty, right? And this is done k-1 times, right? So this is the key aspect of scaling this method. So we have to do this lying and refitting k-1 times to generate k configurations. And this iterative, if the iterative process is slow, then you have scalability issues, right? And Gaussian process is really bad at that. That's why we use random forest, and random forest is parallelizable, and we can speed up this process. So the question is, what happens if you don't lie, right? If you don't lie, then this is what happens. So let's say, again, take this cartoon, and we have here the high uncertainty. If you just blindly sample k configurations, then all the k configurations are going to come from this one region, right? That will result in the waste of resources, because once you sample some configuration here, one configuration here, you know a lot about this configuration. You don't want to lot about this space. You don't want to sample more configurations in this space, right? So you want to go and sample here, 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 right? And by doing this constant liar scheme, you sample from here, and then you lie to the model, its prediction is right. So automatically this uncertainty will go to 0. And then you move to a next region, which has a higher uncertainty. You select at that point and tell the model its prediction is right, and its uncertainty will go to 0, so that it will go to the next region. You see the logic? So this is how you sort of move from one uncertain region to another uncertain region within the same k configurations that need to be generated. Okay, we investigated and implemented 2 different types of strategies. One is the common approach that is used in scaling Bayesian optimization. This is one manager, multiple workers, where the manager runs the search and generate configurations for the workers. So think of all the workers being GPUs, and each worker evaluates a model and give the results back. And all this can happen asynchronously. So some of them can finish at the same time or very closely. So the manager needs to generate or take those results, retrain the model, and then send this back to those workers. Typically, this type of scaling, works for tens or hundreds. And in Bayesian optimization literature, tens and hundreds is a scalable method. But we are after something that in the order of thousands and 10,000s, and these type of schemes sort of have a scaling issue when we move to that sort of scale, and that's where we came up with a completely distributed scheme which doesn't have any sort of manager. All the workers will run the search, which they will do one at a time. But then before generating configuration, they sort of look at all the results of other workers. And note that this communication happens asynchronously. So where each worker sends the data to the other worker in an asynchronous way. So whenever the worker is ready to generate a configuration, it already has the data from all other workers, and it takes all the data and then refeed the model and then generates K configurations. So it's a sort of an extension of this single manager, multiple worker scheme. But here we have to take care of the communication and optimize the communication. And this scales much, much better than this one. Okay, so some examples. So we are applying this to a number of science case studies. And so this is one on sea surface temperature from NOAA SST dataset. And here are some scaling results. So on the x-axis, you have the search time. So this is not the training time. This is the overall search time. So this is the time that we use for the overall neural architecture and hyperparameter search. And with 33 nodes, so we ran this one on Theta, not on Theta, on Polaris or other type of GPU machines on Theta. It's a relatively smaller data set, so that's why we did this on Theta. But this is the scalability result. So on the y-axis, you have the number of unique architectures with R² value greater than 0.96. So 0.96 is sort of the manually generated neural network, and that's the accuracy. So we are looking at how well we can do with respect to manually generated baseline. And then with the x-axis, you can see with respect to the time, with 33 nodes, 33 workers, you can see like, okay, by within an hour, we can definitely outperform what can be done with the human baseline. But then as you keep on running it for 3 hours, with 33 nodes, very moderately sized run, we can generate hundreds of neural architectures that are better than a human-generated one, right? So human can generate only one, and you can think of how much time one can take, depending on the expertise level. But here, with the automated mechanism, within 3 hours, we can, even with 33 nodes, right? So any university have such a type of cluster, and we can do these kind of studies easily, right? We can generate hundreds of models that are better than the human-generated baseline. But here is the leadership class scale. I won't, it's 512 is still not leadership, but I'm just saying, like, if you keep on increasing the nodes at hundreds, you can generate within 3 hours more than 3,000 architectures, 3,000 models that are better than the baseline, right? This is fantastic because now we have the ability to generate diverse models, right? So note the y-axis, unique set of architectures, right? Diverse models that are better than a single model that is usually developed by hand, right? Okay, so this is the architecture that were automatically, the best architecture that were generated. So look at all the nice skip connections, how it came up with the different skip connections. And here is a comparison with the simulation. So it's NOAA is the ground truth, HiCom is the simulation model, which takes 800 core hours per day to do the forecast, and CESM is another simulation model, 30 members, 17 million core hours. And then, if we have the data and we do a completely data-driven surrogate model, we can do this kind of forecast within milliseconds. And you can see those results, it's very close to the ground truth. And in fact, we did better than the simulation, which took hundreds of core hours, the HiCom and CESM, and the accuracy results are given here. So it's in fact, we have more than 1,000x speed up once we train. So that is a training time that we need to take into account. In this case, we spent 3 hours doing all this, and now we can build a model. Now we have a set of models that can do very well than CESM and HiCom, which are which are computation expensive simulations. Okay, now the question is, okay, so we have this capability of generating diverse set of ensembles, right? Now, our question, then we sort of wonder, like, how can we use that, right? So that's where we came with this idea of like, we can use that for uncertainty quantification, right? So here the idea, so why we need uncertainty quantification? Because many science models, we have limited data, and we have always like do out of distribution prediction, and we have to have this sort of assessment of like how good the model is, and build trust. And when we have to deploy this in a loop or in sort of controlling complex systems, we need to make sure that the model is certain about its predictions. And there are two major forms of uncertainty. One is aleatoric uncertainty, which is coming from the data itself. So look at this this figure where you have the data, the original function like x and y. So original function is shown in blue, and the measurements are like, that sort of, there is a noise in the measurement, so you can see that. So this uncertainty that arises due to the noise in the measurement is aleatoric uncertainty. And then you have epistemic uncertainty, which is the uncertainty when you try to predict outside your training data region. Then you have this epistemic uncertainty that says like, okay, I'm going far away from my training data regime. Okay, a promising approach to do that. So what we were doing with the HPC, and scaling and generating ensembles. Then this deep ensemble approach is one of the most robust uncertainty quantification technique, where you say, okay, take the single model, change the random seed, and train it multiple times, and then you generate this ensemble. So note that all of them share the same architectures and the same training parameters, but the things that often change is only the random seed. And you train them, and you generate the ensemble, and then with the ensemble, then you go and do the uncertainty prediction from that. So how do you do that? Is, we did some theory. So essentially, configure each neural network for a regression problem to predict a mean and a standard deviation or a variance, mean and sigma square, right? And once you have configured that neural network like that, then you use a negative log likelihood loss to train that model. Once we have such a sort of a training, then we can do a neural architecture search or hyperparameter search to generate an ensembles. So once we have an ensemble, then the total uncertainty can be written down as a sum of aleatoric and epistemic uncertainty. And we can, in fact, show that it is possible to derive the uncertainty from the ensemble. So long story short, your mean prediction from an ensemble is, okay, so you have a mean prediction from each model, which is a mu, right? And an average of that, a mean of that is your mean prediction. So that is this one. Your sigma squared, each neural network has a sigma squared prediction, right? So that's how we configured the neural network with the log likelihood loss. The mean of the variance is aleatoric uncertainty. That is the data uncertainty coming from the data. And the variance of the mean, right? The variance of the mean, which means that each neural network is going to predict a mean for a given unseen point, and the variance in that is epistemic uncertainty. It's a beautiful theory, and this theory already exists in the variance decomposition, right? So, but if you have an ensemble that can predict a mean and sigma for any unseen point, then we can decompose the uncertainty into aleatoric and epistemic. That is the takeaway. And that has many interesting properties, many useful things. And this is where the state-of-the-art Bayesian neural networks fall. They always estimate, those neural networks always estimate the total uncertainty. They don't estimate the aleatoric and epistemic separately. I will tell you why that is important. So here is the uncertainty quantification on those ensembles that we generated, right? So we already have ensembles. We computed the mean, each neural network is sort of, configured to predict mean and variance. And then this is a 8-week forecast. And you can see with those ensembles, now we can generate, estimate aleatoric and epistemic uncertainty, just as I showed. And from the data, from the model, then we can look at both aleatoric and epistemic on this. And we can see that epistemic is almost zero, which means that all the models in the ensemble more or less do the same prediction. So we are good with models, model accuracy, but we are not good with data accuracy. right? So the aleatoric uncertainty is higher. So this is the scale, and this is visualizing different aleatoric uncertainty. So which means that, there is no point in, optimizing the model here. It is important to go and look at the data and the noise in the data. And that is what these aleatoric and epistemic uncertainties are telling. And of course, here is the mean absolute error. And we can also see that, the model model is making errors. So the more brighter, it means the errors are higher, the mean absolute errors are higher. And that directly correlates with the aleatoric uncertainty, and also to an extent epistemic uncertainty, which means that when a model do a prediction, wherever it is doing mispredictions, you have large uncertainty. And that is trustworthiness, right? When you get the prediction, if you have an uncertainty and you say that my uncertainty is large for my mispredictions, done deal. You are pretty good on that front, right? And that is what needed in many science applications. You want to trust the model, but you also want the capability to the model to say, oh, I'm giving you prediction, but I don't know, I'm not sure about my prediction, right? So that's the key. We also did this with the Bill Tank's team in Princeton, who published a Nature paper in 2019 about using deep neural networks for disruption prediction in fusion reactors. So here is a fusion reactor, and you have a plasma, and you want to see whether it is stable or not. Okay, fine. And they sort of like, they want to predict the stability of the plasma as a sort of a time series. You have number of diagnostic measurements coming into the neural network, and you have to use this to say whether the plasma is going to be stable or not, right? And here is what we did. So we did an automated approach, and each of these points on the x-axis, again, you have search time, and y-axis validation accuracy. And this dotted line is the model from the Nature paper. And when we did this automated technique, we can outperform the Nature paper within 60 minutes of search time, right? More importantly, we can generate thousands of models that are better than the human developed baseline, which is published in the Nature paper. Right? This is amazing, right? So now you can push a button and go and read a paper or whatsoever. Within 3 hours, you have hundreds of models ready for your deployment, right? Of course, we had to do some model selection on top of it, and here is what it is, how these models were trained, and this is the baseline, the human-generated baseline. The automatically generated baselines are not only better than the human baseline, but also they are faster, right? So they are faster to train, and they have better accuracy than the human-generated baseline. And here are some, this shows the model diversity. So these are the different hyperparameters that we used for the hyperparameter search. And this line chart shows, how they are, how diverse these models are. And here is another interesting thing. So this is the snapshot, and this is a manually labeled snapshot. Okay, so the color change from blue means, okay, no disruption, and here someone marked as a disruption, the human-generated, human labeled data. And with the uncertainty quantification in place, so here is the uncertainty that we estimate as a function of time, and we can see that human can say, okay, here is where the disruption has happened, and we can detect that much well in advance, because thanks to the uncertainty. So the uncertainties are saying, oh, something is wrong, model both aleatoric and epistemic uncertainty, they are sort of going up and say, okay, something is wrong before the humans can capture this. Similarly, this one, the human captured this at this point, right? So this blue point, whereas we could do that much well in advance. Like, it's clearly here, it's saying, okay, something is going wrong, something is happening, and then finally the disruption happens here, right? So that's the sort of power of uncertainty, in the sense that we can do this uncertainty as a function of time, and the uncertainty will tell us that something is not right well before it is marked as disruption. We also did that on graph neural networks. So the nice thing about deep ensembles is the generality. You throw any neural network, we can generate ensembles, right? Once we generate ensembles, we can estimate uncertainty, right? We don't have to develop any sort of uncertainty techniques that are specific to the model. And more importantly, these methods, ensemble methods, are a lot more scalable. We can use HPC resources to solve this important problem that is faced by the deep learning community. So essentially, this is a spatiotemporal neural networks, which consists of encoder, decoder, time series forecasting, again, for the traffic. You give a set of current traffic metrics from 8 to 9, and you want to forecast 9 to 10. Again, nice uncertainty estimate, aleatoric and epistemic. And for this work, this is the first time in transportation literature that we showed the uncertainties can be estimated, both aleatoric and epistemic, and it can be shown. So you can see, this is for different locations in San Francisco. Some of them doesn't have a lot of variation, so your aleatoric and epistemic are smaller in the forecast. There are other regions which has higher, higher variations in the traffic, and we can show that, this epistemic uncertainty shown in the blue is very, very small, right? There is no point in going and collecting more data and training this model more and more. But what is important there is the aleatoric uncertainty. Aleatoric uncertainty is higher because the traffic itself in that place is very, very chaotic. It's very undeterministic, and you cannot do much in such kind of system. It's a very highly nonlinear dynamical system that doesn't show any pattern, and that's what this aleatoric uncertainty is capturing. And there is no point in collecting more data, training this model more than what is required. On the other hand, here it shows, oh yeah, there is high epistemic uncertainty for a high traffic congestion. We can do better by improving the model and so on and so forth. This is very, very critical for proactive and reactive traffic management. So with that, I'm sort of towards the end, and this is the DeepHyper software project, and here is the link. And we are working on a number of other aspects of this problem. In particular, the reason why hyperparameter tuning or automated machine learning is not widely adopted is because it's still computationally expensive, even with HPC. We are thinking about like how to do transfer learning across different AutoML tasks, and essentially try to do few shot learning where you say, okay, give the data, can we generate a neural network model directly, right? And those kind of things. So which needs like training a large foundation model kind of thing, but that's sort of work in progress. And we are also exploring the automated application hardware co-design of neuromorphic algorithms, where we say, okay, here are spiking neural networks, here are the application, and here are the hardware, how we can optimize all these in together and sort of extract performance and energy efficiency and so on and so forth. Thanks to the team and their great work. So many of the work that I presented, full credits to the team, and acknowledgements from Department of Energy for funding this research, and the SIDAC institutes, and also Argonne for providing funds, internal funds. Thank you. I'm ready to take some questions.
Thank you. Thank you very much for a great talk. Before we go to the questions, I'll introduce the next BCast. So in 2 weeks, Dan Ernst from Microsoft will be talking about memory-centric designs for modern data centers. In the talk, Dan will touch upon data-driven approaches for setting direction memory architectures. And we'll be looking at 2 different systems, exascale supercomputing and cloud memory disaggregation. And with that, let us start the questions. I think Torsten has one already. You can unmute yourself.
Yeah, if anybody else has a question, then I'm happy to yield. But I have a ton of questions actually, probably longer than we can have. Anybody else? Not yet. Okay. So let me just start. I mean, it's a really interesting idea to take a set of models, an ensemble of models. I've not seen this or considered this before, but there are many other approaches how you could get to ensembles, right? You could do, you could perturb the input. You could actually use dynamically routed models. You could introduce noise in the process itself. I mean, there's so many different ways how to do this to gain a little bit about uncertainty. So how do those compare? Do you have an intuition, an idea? Like you throw one new one over the wall, and have you compared it to all the old existing ones? Is that?
Yeah. So I didn't present the results, but so one of the paper that I cited, in that one, we compared this to several existing uncertainty quantification network, uncertainty quantification methods, single model uncertainty, even like the deep ensemble, just with different random seed and sort of perturbing the model. So the other thing is like you have the model and you do a Markov chain Monte Carlo to sort of perturb the weights and generate the ensembles. So we found that generally deep ensembles, the uncertainty from deep ensembles are much more robust than a single model ensemble. Mm-hmm. There is multiple reasons for that, and there is a huge literature on the deep ensemble side to say like why this is the case. But essentially, the diversity of the models play a major role, right? So if you have a single model where you perturb the weights a little bit, you are still in that local solution, right? So whereas here we are looking at still we cannot capture the entire landscape, but we are targeting different models from different regions and use that to do this sort of prediction. So it sort of avoids model collapse compared to the single model uncertainty, and it's a lot more scalable compared to the Bayesian neural networks, are the neural networks that were that provides uncertainty based on Markov chain Monte Carlo. Because that's sort of like there is a little bit of not a little, it's heavily sequential. So if you don't have a lot of resources, yes, single models are great. Yeah. That's the right approach. But then when we have this, right? So in some sense, we got uncertainty quantification for free, mm-hmm. right? By running this architecture search, we got uncertainty quantification for free. And then we started comparing to those methods and found that aleatoric and epistemic uncertainty estimates are much more robust than single model uncertainty and other methods. So, but again, the uncertainty quantification literature is also sort of growing, right? So there are multiple methods. We didn't do a comprehensive comparison with all the methods, but we stick to the methods that were widely used for benchmarking. We did that on the same benchmark data sets. And sort of came to that conclusion.
Yeah, you triggered 5 more questions, but I will yield to Yannis who has a question.
Yes.
Yes. So I have a question about the complexity of the model. So do you have any measure of complexity in your ensemble? Because so just from experience, usually, especially with skip connections, it's like the more layers you add, the better the model usually gets. So like is this considered, and like how would this compare? Like if I take your combined node hours and would just throw it into a giant model, like where would I expect this giant model to end up?
Okay, that's an interesting question. So so the second part of the question about like, okay, you take all these models and put that together, I don't have an answer for that. I have to start thinking about it. That's a great point. But to answer your first question about the complexity, so the complexity can be measured in many ways, and what we are also currently doing is the multi-objective optimization of the same. So we not only optimize with respect to accuracy, but also with respect to number of parameters, training time, and so on and so forth, right? So a crude way to measure the complexity is, of course, the number of parameters in the model. And now you say, okay, I have 2 objectives, right? Number of parameters in the model and the accuracy. And often this sort of like have a trade-off. The larger the number of parameters model, but then with the skip connections, it can also be anyway, right? So the idea is to have a multi-objective formulation of this and try to optimize both of them and have this Pareto front where we have set of models that will provide you the trade-off between accuracy and the number of parameters, and sort of then we can go and choose. Having said that, here's an interesting thing that we found during the experiments. This is an asynchronous Bayesian optimization, right? So the models that finishes faster with higher accuracy have higher probability of going back to the search and biasing the search towards that region. And what happened, thanks to this asynchronicity, we started seeing that the search has sort of a tendency to build smaller models with higher accuracy, or models that can train faster with higher accuracy, right? So we cannot guarantee that, But that's what we found. Like, once we make this problem, like, if you start, if you don't give max, if you can set a maximum evaluation budget, right? So maximum budget time to train a model. If you train a model for 1 hour versus 10 minutes, so you set a cap of 10 minutes. Each evaluation can take only 10 minutes, and you start seeing like, okay, after that you go and look at what type of models it came up with. It came up with models that can train faster with high accuracy. On the other hand, if you give 1 hour, you don't see that effect. So it's thanks to this asynchronicity that is part of the algorithm. But that's a sort of more an empirical observation. But the right methodological approach is to formulate this as a multi-objective optimization and solve this as a Pareto friend. And we do have an algorithm which is part of the software. We are using it for energy efficiency and performance for spiking neural networks. And we are also looking into this sort of parameters. So does that answer your question? I don't know the answer for the second part. How that will look like.
That's actually, yes, the feedback loop with the asynchronous training makes a lot of sense. Thank you. I have one other question regarding your multi-point sampling, and that is, so when you do the constant lying, basically every point, first you lie, and then you have a second point, then you have to lie twice, then you have to lie 3 times, and so on. So how well are these secondary and tertiary points when you compare it to the actual evaluation? So if you take your uncertainty estimation of the lie distribution to the then evaluated distribution.
Yes, so it depends, right? So in the beginning, it will be bad. In the beginning, the lies will be bad, right? As the search progresses, the lies will get better and better. So because the model has seen multiple regions, it has ability to have, it has ability to sort of, get better with respect to prediction. So towards the later part of the search, once it learns, then the lies are becoming better and better. Whereas in the beginning, it's completely, off.
Okay.
Yeah, no, I just want to say thank you. That makes sense.
Yeah, I think if you have ideas on like how to combine these ensembles into one gigantic model, I'm happy to touch base and not only that, just any other related ideas. I would love to chat.
Okay. Do we have any other questions? Langve, let me unmute you.
Yes. So I have a small question. So is the random, is the weights of the neural networks also part of the random search in the part of random search space?
No, not at all. The weights of the, so I told you about the lower level problem, right? So the upper level problem is a Bayesian optimization, right? Lower level problem is stochastic gradient descent or whatever the variance. So whatever the optimizer, in fact, we choose the optimizer as one of the hyperparameter, but then we train the neural network using stochastic gradient descent variance, right? So the weights are not random. They are initialized random, but and the type of initialization strategies, you can make that as a hyperparameter and search through it. But essentially, the neural network weights itself, they are trained in a usual way, like what you typically do with a neural network. Right, so there is no randomness. I mean, we don't use any random search for that because SGDs are the best for the job, right? But then the upper level problem is the Bayesian optimization problem that sort of goes and turns different levers and see which one works well for the lower level problem.
Okay, thanks. So how many hyperparameters can we put into the search space in this kind of method?
So we tested up to 50. It can go even more, in particular with respect to skip connections, right? So skip connections are all binary variables, 0, 1, right? So if you have, if you have 3 layers, right, you can connect the first layer to the third, right? That's one skip connection. If you have 4 layers, then you can connect 1 to 2 right? So 1 to 2 is default, right? So 1 to 3 and 1 to 4, right? If you have 6 layers, then it's like 1 to 3, 1 to 4, 1 to 5, 1 to 6. Those are all possible combinations, right? So each one is modeled by a binary variable. So so scaling definitely helps. So if the increase in the number of parameters, the scaling becomes a lot more crucial. So we tested up to 50, and we are pushing the limit more to hundreds because of the skip connections and so on and so forth.
Okay, thanks a lot. Oops. Go ahead.
Great. So any other questions or? Yeah, I cannot see other questions. Thorsten unfortunately had to run, but from both of us, thank you very much for the great talk, for the insightful Q&A session, and see you all in the next BCAS in 2 weeks. Thank you.
All right. Thanks, everyone.